Yes, if actually if you have doubt, you can post it here. I will check and reply to your questions. Otherwise, you can if everyone is talking, then it will be like a echo will be there and chaos will be there. So you can unmute your mic and ask one by one, and also you can put on the chat box also. So no problem. The classroom doubt that if after while you are revising your class notes, okay, if you have doubt or during the class also, those who cannot ask during this 1 hour, okay, they can ask there also. Okay, so that is why the classroom Google Classroom is created. Yes, in the comment box also. So I will share my screen so that you can. I can tell you the. Okay. Hello everyone. Again, uh, we are going to discuss the mathematics one, MA 101. I am your course instructor, Dr. Jagannath Rai. You can always also contact me through this email. Okay. So the course is actually a 3 credit course. So weekly we have 3 courses. Okay, no lab is there, so that is why 300. So there is a maximum possible that we can have 42 lectures, but let us see what will happen if the time permits. Okay, so the basically it is divided into 3 modules. First one is matrix theory, then differential calculus, and then ordinary differential equations. Okay. Suggested readings, R.K. Jane Younger. Okay, I will share one of the books. I will share these 2 books, Basic and Engineering Mathematics. Higher Engineering Mathematics by V.S. Grewal. Okay. So, okay. From the day one, we have to be serious. Okay. Because just after the 3 weeks, we will have one 15% mark containing. We will have minor one. After 6th week, we will have mid. So there will be a continuous evaluation. Okay. So there is no scope for we'll read it later. We'll do it at the final. So we have to be careful continuously. And also there is no request that since you will be having minor exam, so you may request for cancellation of class, but that is not actually encouraged because minor exams will be held during the evening time. After class hour, minor will be held. Okay. So the module 1, matrix theory. Okay, in order to go to the directly to our sessions, so we have to recall our school level mathematics, scalars, right? See, those are constants, only have a magnitude. But vectors, those who are having direction and magnitudes. Direction and magnitudes. Now we have seen it as in the 2-dimensional space. Okay, a vector like this way, or this direction. Okay, I direction, J direction, B is a vector. We have seen like this. Okay. Now we have also seen the vectors in the three-dimensional also. So this is ith direction, jth direction, and kth direction. Now the idea of these vectors and points in the two-dimensional space and three-dimensional space are generalized. So how do we generalize these things? Because it was observed that during the 19th century, some mathematicians have observed that this idea can be generalized to higher dimensions also, fourth dimension, fifth dimension, and so nth dimension, okay, up to finite. Okay. So some famous mathematicians like Gale, okay, Sylvester, and Hamilton, they have realized the concept of points and vector could be generalized. So they have actually started to define uh, the object. The only difficulty will be it will be like more like analytic, abstract sense, okay, analytic sense rather than geometric. Because up to three dimension we can visualize. Okay, after that we cannot visualize. Okay, fourth dimension we cannot visualize. But the same concepts, same operations, okay, will be applicable in the higher dimensions also. So, so what we do, we define n tuple. It can be written as in this form also, or it can be written as, that means here it will have n components. N components. N components. If we consider about three dimension, then we have x, y, z. So this is actually a three tuple. Okay. And in the two dimensional x comma y, it is a two tuple. Two tuple. Okay. Now, as we know that this two-dimensional space can be written as in this form. Cartesian product of the real number. R is the set of real numbers. Okay. And three-dimensional space can be written as this form. So when we have n tuple, that means a point in the n-dimensional space will be a member of R cross, R cross, R. Okay, where n copies. So this is actually Rn. So we'll call it Rn. Sometimes we'll write it like in this way also. Okay. So now we are going to generalize the idea of vectors and points in higher dimensions. Okay. What is n space? Okay. In formal terms, a vector in n-dimensional space is an ordered tuple. Now, if you remember that the identity vectors that we have okay, I, J, and K. So I equals to, we have written 1 0 0 unit vector in the x direction. J can be written as 0 1 0. K can be written as 0 0 1. Okay. So similarly, a vector A, okay, when we write a vector, hereafter we'll remove this arrow. Okay. When we say a vector in a n-dimensional space, that means it will be an n tuple. Okay, so that is understood by the, whenever we are saying that it is a vector in the n-dimensional space, then we will understand that this means A is actually A1, A2, AN. Similarly, B is B1, B2, and Bn. Okay. Okay. Now the addition in n-dimensional space, okay, that can be defined as by this operation. Just a minute, guys. Okay, guys. Sorry for the disturbance. So where were we? So let us, okay, come back to our discussion. Since all the points are, okay, in this n-dimensional space, it will have n components, okay, n components, and the addition of two points are defined by, okay, 2 points are component wise, A1 plus B1, A2 plus B2, and so on, An plus Bn. In this way, we will define. Similarly, multiplication by a constant, A is a constant, is defined by, in this equation, in this relation. Okay. Now the zero vector, okay. Zero vector in the n-dimensional space is actually written as 0 equals to n component of n zeros will be there. Okay. N zeros will be there. Okay. So, just like we have defined the length or the magnitude of a vector in the two-dimensional case, here also we will define the length of the vector that is defined by in this equation. Okay. Earlier we had used like absolute value, there is modulus value, but this symbol is called norm. This is called norm, okay, for a higher dimensional case. Okay. So similarly, a unit vector can also be found in the same manner when the norm is 1. That means for given any vector A, we'll find out the norm and we'll divide the vector by the norm, then it will be a unit vector, just like we have done in the two-dimensional case. Okay. Similarly, for any given vector, A is given in this way.
Sir, what is the direction of zero vector? Sir, as it is zero, it has no any length. Then how can we define its direction?
No. Here, in whenever we are starting here, so we will not be bothering about the zero vectors. What is the? Do you remember what is in two-dimensional? What is zero vector?
Sir, zero vector has zero magnitude, but how can we define its direction?
Here we don't bother about this direction actually.
Okay, sir.
Okay. Anyway, so unit vector we can for given any vector we can define a unit vector u after finding the magnitude. Okay. Now the product of two vectors. Okay. These are just some difficult names. You don't have to be don't be afraid with these names. Okay. Just look at the operation, component-wise multiplication and the addition.
So can you please go to the last slide?
Any doubt?
So just 2 minutes, 1 minute.
So we will get the PDF of this, right?
Yes, everything you will get.
Yeah.
Everything you will get. So these are just basic introductory, okay? So if you do not get it at once, okay, in the first reading, so you don't have to be bothered. These are actually defined, these are actually base for the next, what I am going to define in the next one. So these are actually useful. Okay.
Sir,
Yes.
sir, in n-dimensional space, what are the reference coordinates called as? Like they are named as x, y, z, so on, or something. They have another names.
No, the same thing. You see here, E1. Oh, you're talking about that XY plane, right? This is
No, sir. In 3D plane, we call it as x, y, z. No, sir. So then, in n space plane, what are the reference coordinates, or what are those called? Are they having any name?
I don't think there is any particular name is there because after this three-dimensional we cannot visualize. Okay, so we are not calling any x, y, z or t. We have not seen like this way, right?
So then, how to define A1 means component of A on any axis, or like how to define A1?
Okay, let me write down. Suppose R is a matrix. R is a set. Okay, R real numbers 1, 2, and minus is also there. Okay. So similarly, if you write R cross R and R, so what will be x1, x2, x3, and x4, such that xi belongs to R. Okay. An element of this form, okay, after taking the Cartesian product of all these 4 times. Similarly, we can go for 5 times. Okay, we can define it like 5. And so on. Okay, n times. N will be decided by depending on the problem we are having.
Sir, means if you have, so in 3D space, if you have A is 3 to 3 comma 2 comma 1, then we say 3 is the component of A along the x-axis.
Yes, 3 to
Then
1.
in ND space, what A1 is called, like it is component of A in some axis which is present in n space, or like does it have any specific name, that component one?
You
In
can call
3D
it
space,
A. Okay.
like x coordinate we have in 3D space, then in ND space does that have any name or?
No, there is no name. There is no name. But provided that A1, okay, suppose you are having different sets. Here I am taking one same set. That is why you are making it. It is difficult. Suppose you are having R1 is a set. Okay, R2 is a set. R3 is a set. R4 is another different set. So what you will write? X1, X2. That is, this set is defined as X3 and X4 such that Xi belongs to Ri. Right?
Yes, sir.
Okay. So the first component here, from here, it will belong to the first R1. Then the second component will belong to the second one, R1. Second R. Okay.
Okay, sir.
This order will be maintained. Okay.
Okay, sir.
So we move forward. Okay, the standard inner product, these are just definitions. The idea is actually, here also we'll define the orthogonal vectors. Okay, when the dot product is 0, then we will call it the orthogonal vectors. Okay. So after defining the vectors in n-dimensional space, okay, now we are going to define the vector space. Okay, so vector space, it is aimed to distinguish between the scalars and vectors. Okay, from hereafter, we will call scalars will be a single digit number. Not single digit number, they are constants. This is also scalars. This is also a scalar. Okay, so scalar will be constant, and this will be selected from real numbers. Okay. In our study, we will consider only real numbers. Okay, for higher studies, scalars can be complex numbers also. Okay, so vectors will be like n component, n tuple. Okay. Now, in order to study the idea of vectors in higher dimension, we have to define a mathematical structure with 2 operations. Okay, V is a non-empty set. V is a non-empty set. It will have at least one element. Okay, then this set, along with these 2 operations, is over the real number set is called a vector space if it satisfies the following 10 assumptions. So the assumptions are like this. Okay. The first one is vector addition. For any given 2 vectors, x1 and x and y, from this set, suppose x and y belongs to B, then it should be closed under addition. That means x plus y, okay, v. It should belong to in this way. So that is, this property is called closure, okay, under addition. Closure under addition. And similarly, the second property is, for any x and y belongs to B, we will have x plus y equals to y plus x. That is called commutative property. After that, for all x, y, and z, for three vectors in B, you don't have to write anything. Okay, because I will share everything, this recorded video and the PPT also through Google Classroom. So you have to just listen.
So can you please explain vector space again? I didn't quite understand that.
Okay, vector space is actually a mathematical structure V plus dot, and say this set over the real number set, because the constant that we are selecting, these are from real numbers. Okay, a vector space over this is a mathematical structure, a non-empty set along with two operations plus and dot. Okay, this set will be called, this whole set, okay, will be called a vector space over the field R if it satisfies the 10 properties. So all these properties has to satisfy. Then only we call that P plus dot is a vector space over R. Okay. So it will have to
So
satisfy
the
all
V
these.
is the constant or the vector?
Which one? K?
No, the V, like, is a V or
No, V is a set. V is any set. V can be
Okay.
singleton 1. We have to test whether it is V can be singleton 0. V is just non-zero. Sorry, non-empty set.
Okay, thank you, sir.
It is non-empty set. Okay, after once it is, we have to check for given any set, we have to check whether it is satisfying or not. So we have to go to the next example. Suppose V is 1, singleton 1, then whether it is a vector space or not, we have to verify. Okay, let us consider the first constraint, first assumption. Suppose 1 belongs to V, then 1 plus 1 equals to 2, but this does not belong to V, so it is not satisfied. So in order to V to be a vector space, it has to satisfy all the 10 constraints. Yeah, 10 axioms. This mathematical structure should satisfy, but it is not satisfying the first one. Also, this one, the sixth one, will not be also satisfied. For any k, 2 into 1 equals to 2, which does not belongs to V. So the first one and the sixth one are not satisfied. So the option A, that is not a vector space. Singleton V is not a vector space. This is not a vector space. However, the second one, if we take V equals to 0, then whether it is a vector space or not. Now, if you check all the properties one by one, then you will understand that 0 plus 0 is 0, belongs to V, because V is 0 here. 0 plus 0, again it will be 0 plus 0. Commutative property is also satisfied. Similarly, you can. So this is actually trivially satisfying everything. That is why this vector space is called trivial vector space. a trivial vector space. Now we will be seeing another example. So that is a trivial vector space. Now we'll see another vector space, a different, non-trivial vector space.
So,
Suppose, yes,
so can you explain example one, sir?
example 1. Remember the first constraint is if x and y belongs to V, then x plus y must belong to V. Okay, we are not telling they are different. Yes, the right is the property is if they belong to there, then their addition, okay, must belong to V. But if we select 1 here, what we see 1 plus 1 equals to 2, but this does not belong to V. Since the first property is not satisfied, so we can conclude that this singleton V, singleton 1, okay, this is not a vector space. Is that clear?
Yes, sir.
Sir,
Yes.
sir, I have a doubt. Sir, what if there are four numbers, four elements in that set,
Okay.
and means unless a negative number is there, negative element is there, then only first condition would be satisfied, no, sir. Like we need to add everything, and that set it should be included in the set.
No, it is not necessary for that.
Sir, when we add all positive numbers, it would be more than those numbers, right, sir?
No, see, we are starting actually abstract sets. These are not necessarily numbers. Sometimes, okay, sometimes we'll have a vector space of collection of different. Okay, all are where fi are continuous numbers, continuous functions. Okay, continuous functions.
Okay.
Okay. So this is actually vector space is a generalized sense. It is not only it is not limited to the number system only. Okay. These vectors can be our functions also. It can be your matrices also. Okay, matrix also. The elements of the vector space.
Then if we add that whole set, means elements of continuous functions,
Okay.
like if
Now you have to tell me whether f1 plus f2 are continuous. Suppose given f1 and f2 are continuous, then whether the addition is also continuous or not.
yes,
Yes, sir.
Yes, then it will belong to the set. Okay. Similarly, other properties we have to
yes, I got it.
verify.
I got it.
Okay. Now, a non-trivial vector space. Okay. Consider the vector space positive real numbers. Okay. Now the addition, what we do? Well, normally what we know is 2 plus 3 is 5. But here, the addition is defined as like this way. 2 plus 3 is 2, 3. We are not selecting. We are just writing 1 by x beside y. We are not adding or we are not multiplying anything. Okay. It is not 23. It is just 2, 3. We will read it at 2, 3. Okay. These are just mathematical operations we are defining in that way. Okay. And the scalar multiplication, we are writing it if it is k into kx equals to x to the power k. Then whether it is a vector space or not, we have to verify all the properties. No. Okay. Since all are positive real numbers. Okay, so the first vector x greater or equals to 0, the second vector y is also greater or equals to 0. Then x plus y, that is defined by definition, it is xy, which is since both of them are positive, So this quantity will also be positive. Hence, the sum is this quantity is actually positive real number. Real number. Okay, which is belong to the set by the definition. Okay, V is the collection of positive real numbers. So we are getting one positive real number. Okay, their addition is a positive real number. So similarly, we will get all the properties verified. Okay, you can check, and if you have doubt, you may ask me later. Okay. Now, just like we have x belongs to A implies for x belongs to S. Suppose S is a subset. A is then what? For x belongs to. Then we say that A is a subset of X. Similarly, for a vector space, okay, for vector space, we will have a subspace. Vector subspace. Okay, first of all, it has to be, suppose V is a vector space and W is a subset of V. Okay, W is a subset of V. Then W is called a vector subspace if W plus dot is a vector space over the same field R. Okay, over the same field R. That is, now in order to check whether a given set, whether the set is a subspace or not, we have to verify two constants, two conditions. If we check these two conditions, the other 8 conditions will be automatically satisfied. Okay. So we can check whether the given subset is a subspace or not. So we are having one subset of R3. So this is actually a subset of R3. A subset of R3. This is a subset of R3. Okay. Now we have to check. We have to check whether S is a subspace or not, because it can be proven that R3 with usual plus and dot or with usual multiplication and with usual multiplication and visual definitions, visual operations. Visual operations. What I gave you in the previous slide, okay, this is unusual addition. Okay, this is a special case. This is unusual multiplication. Okay. So let us check whether it is a subspace or not. So what we have to do, we have to select two vectors. Okay. Then we have to check whether the addition is also a member of the set or not. So let us check whether. Okay. In R3, we know that the addition can be defined as component wise. Okay. X1, X2, X3, and if it is Y1, Y2, and Y3 belongs to R3, then the usual addition is X1 plus X2. No, sorry, X1 plus Y1. We have to define X plus Y. This is, suppose this is X and this is Y, then X plus Y will be in this way. x1, y1, x2, y2, and x3 plus y3. So the same operation will be applied to the substrate also. So if it is belonging to the set, and also after multiplying with the constant, if it is also belonging to the set, then we will tell that the given set, the subset, is a subspace. We have to check, in order to check whether it is a subspace or not, we just need to check these two criteria. Okay. Now, there comes the actual start of our course. So these are the just basic preliminary introduction so that we can understand the vector as a different perspective, okay, as an n-tuple. So given n vectors v1, v2, and vn, are vectors in the space V. That means v1, v2, vn belongs to V. They are vectors. Okay. Then c1 v1 plus c2 v2 plus cn vn is called a linear combination of vectors where c1, c2, and cn are real numbers. Okay. Now let us check how to write a vector, a linear combination of vectors. For given any vector 3, 0, 1, 4, and 4, -2. Now if we write down 3v1, we are selecting these are arbitrarily. Okay. You can select this one also. So because we are telling about it is a real number, so we can take positive, negative, and 0 also, so that we find out the resultant. So in this way we can write 2, -28 is a linear combination of the given 3 vectors. Okay. For different selection of these constants, okay, we will have different linear combination. Okay. Now the linear combination idea is introduced to define whether a set is linearly dependent or independent. Okay. We have a collection of vectors x1, x2, and xn. These are called linearly independent if the only constants satisfying the equation a1 x1 plus k2 x2 and ... plus kn xn is equal to 0 will give us k1, k2, and kn all are 0. Otherwise it will be linearly dependent. Not independent means linearly dependent. Okay, not independent, we'll get, that means at least one AI is non-zero or linearly dependent case. Okay, this is not part of the linearly dependent. So let us check whether it is okay for given any vector v1 1 0 0, v2 is 0 0 1 0, and v3 is 0 0 1. So by definition we will select some constants a1 v1 plus k2 v2 a3 v3 equals to 0. Okay. So A1, we'll write it 1 0 0 plus K2 0 1 0 plus K3 0 0 1 equals to, whenever we are writing these vectors, okay, so this vector is actually, this right hand side vector is actually 0 0 0. Okay. So here, please remember this thing, that we are writing 0 here, that means it is a, depending on the size of this, whether it is 2 tuple or 3 tuple, it will be, suppose this is n tuple, x11, x12, or this vector can be written as, suppose a1, a2, an, then we will have this vector as 0 0. Okay. Otherwise it will not be satisfied. So we have 0 0 0. So what we have now, k1 0 0 plus k2 0, k2 0, and k3 0 0, k3 equals to 0 0 0. So from this equation we will equate that, we will solve this equation. So it will give us only k1 0, k2 0, and k3 0. So the definition is, so V1, V2, and V3. This V1, V2, V3, okay, here are linearly independent. Okay. So if any one of these ki's are non-zero, then it would have been a set of linearly dependent vectors. Okay. So let us see another example where, so let us write down k1 v1 plus k2 v2, v3 v3 equals to 0. Take the linear combination. Okay. So v1 is this one. Okay, 1. Actually 1 1 1 plus k2 is 2 minus 1 4 plus k3 is k3 into 5 2 7 equals to 0. So what we'll have, a1, we write it as a column form. That was 2 1 1, a2 2 minus 1 4, so that we can understand the equations easily. k3 5 2 7 equals to 0. So we will get 3 equations with 3 variables. a1 plus 2k2 plus 5k3 equals to 0. Instead of 0, we will write it 0 0. So k1 minus k2 plus 2k3 equals to 0, and a1 plus 4k2 plus 7k3 equals to 0. Okay. So we have 3 variables, 3 unknowns. And 3 equations. But since the right hand side is 0, so we can write it like this way. We can write it k1 equals to a2 minus 2k3. Okay. So we'll substitute these values here and here. So we'll get a2 minus 2k3 plus 2k2 plus 5k3 comes to 0, and which will give us k2, 2k2, 3k2, and minus 2k3 plus 5k3, 3k3. So here we will get k1 plus k2 is equal to 0. k1 is sorry, k2. k2, k3. k2 equals to minus k3. Okay. And from here, what we'll get? So for k2 equals to 1. So if we assume k equals to 1, we will get k3 equals to minus 1, and k1 equals to here 1 minus 2 minus 1, that is 3. So all the constants k1, k2 and k3 are non-zero. So basically they are non-zero. Okay. In the previous example, they were uniformly zero. They have become zero from these solutions. We have taken zero. But here, because we are having such a situation, they are equal. But on assumption, they are actually non-zero. So this will give us that the vectors, given vectors v1, v2 and v3 are linearly dependent. Since ki is okay, at least one ki is non-zero, that means we can write it as linearly dependent. Linearly dependent vectors. Okay, so I will stop here today. Okay, I will give you some task.
So can you for once explain the linear combination briefly?
Okay. Linear combination is just, it will have for given any vector, any n vectors. Suppose we are having 1, 2, 5. For any arbitrary, it is in R3. R3, suppose our vector spaces are now R3. Okay. So this can be written as, okay, let us write down 1, 2, 5 in a column form. So 1 into 1, 0, 0 plus 2 into 0, 1, 0 plus 5 into 0, 0, 1. So this vector, this particular vector, okay, is, we call this vector, we call 1, 2, 5 is a linear combination of these three vectors, this one, and this one. 0, 1, 0 and 0, 0, 1. These three vectors. So this is a linear combination. Now if you look at any other vector, okay, you can take it, any other vector that can be written as the linear combination of these three vectors, because these three vectors are actually standard vectors of R3. Okay. For any other case, this was a particular case where we have taken non-trivial vectors. This is a vector v1, 3, 0. This is another vector v2, 1, 4. And this is v3, 4, minus 2. So what we are having here is actually Note that C1, C2, and Cn are real numbers. Okay. So any linear combination, okay, for any values of this theory, okay. So here we can consider C1 as, we are not fixing anything. Okay, we are selecting just, this is C2 and this is C3. This is V3, or it is already V3 is there. So V3. So once we multiply these things, okay, so this will become 9, 0. After that 7 into 1, 4, this is becoming minus of 7, 28. Since we are multiplying with 0, so it will become 0, 0. So after that, this one, we will have this vector. We are having this vector, okay. Now if you write down this vector as 2i minus 28j. That we have learned in our school mathematics. The same thing. Okay, we are not bothering about this I and j's. We are just bothered about. Okay, we are interested in this order n tuple. Here it is 2 tuple. Okay. So if we consider for any particular, this is because some particular C1, C2, C3 have been selected. That is the reason we are having 2, 8. Now, the linear combination will be different. Okay, if you select this, select some different. If you select some different, suppose C1 equals to 1, 130 plus 230 to 1, 4, 1, 4 plus 3 into 1, minus 2. Then what will happen? It will give another linear combination 3, 0 plus 2, 8 plus 12 minus 6. Then what will have? 3 plus 2 is 5, then 12, 17. 0 plus 8, 8 minus 6, that is 2. So this is another linear combination. Combination of these 3 vectors, V1 and V3. Is that clear?
Yes, sir. Yes, sir. Thank you so much.
Okay. So I'll stop here. Tomorrow we have class at, I think at 8 a.m., right? So for every different classes, I have sent you the different Google Meet link. Okay. So use those links for every week. For every other day, I will not send. So okay, I'll stop here.